On the Lavender team, my team members are Matthew Duck and Morgan Younger.
Do you mind taking this?
Outline for our presentation, I'll be going over a background, previous work such as necessary step, sign, etc. Experimental results for the proportional controller, and my conclusion. Water absorber station. This station involves a manometer and Coriolis that used to measure the water flow of the system in the UTC. Here's the actual image of the rotators and the manometers and the water Coriolis meter that is used in UTC for connected to our LabVIEW online. Here is an SSOC of the water flow system that we have, where we got our gain, dead time, and time constant. Here's our FOPDT of our upper and lower slope, and our values that we got here for dead time, gain, and time constant. The frequency response, after we got the results for our frequency response, we found the amplitude ratio and the phase angle with these equations here. The amplitude ratio, which is the amplitude output over the amplitude input in percent pound per minute, and the phase angle, which is our time between our peak time and output peak divided by our time over time between the peak and peak times 360. This is the Bodie plot that we got from our amplitude and amplitude ratio and the phase angle. This was the amplitude ratio. The next slide will be the phase angle. For this one, our gain was 0.3 order. All of them were first order. FU 2.2, KC 10.8, tau 1.9, and TO 2. And as you can see, our the blue diamonds are our actual experimental data. The red line is the model for our data, and the red lines in between our blue diamonds is our error, our uncertainty. And here's this same Bodie plot before a phase angle instead of the ratio. And as you can see, our errors were a lot smaller than our amplitude ratio graph. Here's a sine model, first order, that we've all been working on. This is the example that we use in order to find our actual experimental data. As you can see, the input signal is the blue line, the output is the red. This is what you should get for our experiment for our sinusoidal line. Here's the experiment that we did at 0.02 hertz. Here it's completely sinusoidal. Nothing's going to steady state or going constant. The average for the amplitude ratio is 0.3, and for phase angle is -36. And as we continue forward, our phase angle gets greater, and our uncertainty increases as well. Here's at 0.5. I just did these two, but as it increases, the output continues to come straight and gets to steady state. Here's our root locus model. We use our same values that we got from our frequency response, which is 0.21, 2, and 2. Here are the results for our root locus. We put in the different values of 0.3 to 0.5, etc., to different graphs to get a different experiment for each one. Proportional load controller, we use the same information that we got from our SSOC and from our root locus to use for our proportional load controller. This is a data we got for critical gain experiment. And in here, the lower the KC, the greater the offset was. And you can see that it had a settling time here, but as the KC increases, it continues to oscillate, the settling time goes away. And this graph here is monotonic. At quarterly decay, it's starting to have a little more sinusoidal, and the offset decreases a lot. And ultimate decay, this is where it continues to oscillate and it never settles. So the higher the KC, the greater the oscillation. In conclusion, I went over our old experiments, SSOC, frequent response, floating plot, pre-locus, and our current experiment, the torsional control model.
I'm going to present the week 12 from the beginning until the week 12 for the Ivory team. We have the absorber water flow system. My teammates are Joshua Ware and Justin Holt. So for the outlines, I'm going to describe the system, speak about the previous works, the SSOC, FOPT, the frequency response, the alternative methods such as the relay feedback, and the root focus. Then have a look at the results for the model of the proportional only controller, and then the experimental results of the same proportional only controller, and then a brief conclusion. So our system is, like I said, the absorber water flow system. The input is opening valve in percent, and the output is the water flow rate in liter per minute per person. This is our system, and this is what make us measure the water flow, the various flow meter. So we tried our system. So I redid an input of 50% to have an example of the SSOC. I also redid the SSOC experimental graph. It's only from 50% until 62% of input, which is covering my output values, which are 8 to 12 liter per person. This was the SSOC graph that was given to us for this system. The FOPDT graph that was given also to us, the input model, input value, output model, and output value. So on the FOPDT that was given to us, we could find the gain that was 0.21, the dead time that was 2 seconds, and the time constant tau that was 2 seconds. On the previous work, for the frequency response, our gain was 0.19, and the ultimate gain was 135.07. On this graph, you can see the amplitude ratio from experiments and the model of the amplitude ratio. The phase angle and the model of the phase angle are on this graph. The FU value was 0.19 hertz for our system. This is a pretty recapitulation of our values. The relay response was an alternative method. I tried to redo, I was in charge of the alternative method, and I tried to reduce the KCU because our average doesn't fit with our other datas. So then we covered the root locus. Here on this graph, we can see that this part is a critical damping. Here is all the cases values that are that gives under-damped response. The KCU here gives us a decay ratio of 1, while for critical damping the decay ratio is 0. For quarter response, quarter KC, the decay ratio is 0.25. So again, from this root locus, we can see that our gain was 0.21 liter per minute per person. The tau was 2 seconds. The T0 was 2 seconds, and we selected a KC that was 0.0285. So all the KCD, KC500, KC10, and K2D corresponds to different angles on the plot here. So then for the proportional only controller, we had an Excel file and we had to switch the KC values to find to analyze the response of the system. The minimal reasonable value of KC for our system is 0.31. It gives us a decay ratio of 0. You can see that the system is not oscillating, which is the main point of the critical region. Here we're on the quarter, so we can see that it's a quarter because here when we divide this distance by this one, it gives us 0.25. And this is the ultimate version where we have a KC called the KCU. We can see that the response is oscillating and it never settles. Here is a brief recap of the parameters that we used for this experiment, this model experiment. So for the settling time, we can see that the different regions react differently. On the ultimate regions, it never settled down, so it never settled, so I didn't put the values. On the quarter, we can see that the settling time is way longer than the critical region. For the offset for the critical is bigger than the quarter.